Okay. So, in the previous class we were discussing this joint moments, rather this moment generating function, right. We start from there again. There will be little overlap, but there is nothing wrong if there is little overlap with the last phase of previous day's lecture. So, we are given two random variables as before, x, y, jointly random, then we define this function phi. Maybe we can put a phi prime. I will tell you why I am putting a phi prime. S1, S2 as the expected value of e to the power S1x plus S2y. Now, listen, earlier we had a situation where S1 was equal to j omega 1, S2 was j omega 2, and the entire thing was called the joint characteristic function. It was written as phi of omega 1 omega 2. Since j omega 1 is replaced by S1 here and j omega 2 is replaced by S2, okay, and j is missing on this side, okay, I am giving it a new name phi prime. Okay, there is only difference. This is called the moment generating function. We have already seen what is a moment, joint moment, that is x to the power r, y to the power k, its expected value of this product is called the joint moment of order k plus r equal to say n, right. Now, this function will help us in getting those moments of various orders. Okay. To understand that, let us first do this. This is an exponential, right. So, S1x plus S2y, you can even call it z. So, e to the power z, you expand e to the power z into a power series. We all know what that power series is. There will be a summation of terms, an infinite summation actually, and the expectation is a linear operator. You can apply expectation on each of the terms in the summation separately, right. If you do that, that is, first you have expected value n equal to 0 to infinity z to the power n factorial n. This is the exponential series, okay. And then I will apply this expectation operator on each term in this summation. Factorial n is a constant, so it remains outside. Okay. Then what happens? That is, E. Now, we know what is z. Z is this factor. So, replace z by its actual form S1x plus S2y whole to the power n. Now, S1x plus S2y whole to the power n is actually a binomial series, okay, of n plus 1 terms. Again, that can be, so I can expand this term into its binomial series. So, I get another summation, but unlike the outer summation, that will be a finite summation now, because there are total terms equal to n plus 1, and again expectation can be brought inside that summation and can be applied on each term present in that binomial expansion, right. If I do that, what we get is this. There will be k. So, k should be from 0 to n, total number of terms is n plus 1. Okay. We know that binomial series n k here, factorial n divided by factorial k into factorial n minus k. Okay. Expectation operator does not work on it, because this is not random. Then there will be this product S1x whole to the power say k, S2y whole to the power n minus k, out of which S1 and S2 can be separated out. Okay. So, we get E working on x to the power k, y to the power n minus k, and again S1 to the power k, S2 to the power n minus k. You see this moment is coming here x to the power k, y to the power n minus k, its expected value. Summation of the two powers is equal to n. Okay. So, it is a moment of nth order, right. Also note one thing, there is a summation over n 0, n equal to 1, n equal to 2, up to n equal to infinity. Now, for each n, for a particular n, you have got this summation where total number of terms is n plus 1 first, and then remember for that given n, I mean powers of x and powers of y in this summation, they should be such that the total of the summation of those two powers is always equal to n. So, if n is 4, you can have 0 here, 4 here, 1 here, 3 here, 2 here, 2 here, 3 here, 1 here, and 4 here, 0 here, right. You cannot have anything else. So, this is one thing you please remember, because subsequent derivations will need this property. So, for a particular n as chosen from outside, okay, we will have only those powers of k and n minus k, those powers of x and those powers of y. So, that summation of those two powers is always equal to n. Okay. So, this is what we get as the moment generating function for x and y. Okay. Now, I erase this. As I told you, this nth order moments are present. So, maybe if I expand it a little bit, you will see the various moments are coming up. For instance, you start with n equal to 0 first. So, 1 by factorial n is 1, n equal to 0 means only one term in this summation, that is k equal to 0. Okay. So, that will give rise to what? Basically, that will give rise to 1, S1 x to the power 0, y to the power 0, okay, and then S1 to the power 0, S2 to the power 0, and this 1 here. So, that 1 and 1 by factorial 0, that is 1. So, first term for n equal to 0 is 1. Then take n equal to 1. N equal to 1 means in this inner summation I have got two terms, one is for k equal to 0, another is for k equal to 1. So, for k equal to 0 first, you have got this term S1 to the power 0, that is 1, but S2 to the power 1. So, S2 similarly here e of y, x to the power 0 is 1. So, e of y, okay, and 1 comma 0, 1 0, that will give us 1 only. Okay. So, you will get one term as E y is 2 and E y is similarly now put k equal to 1. So, x to the power 1, but y to the power 0. So, E of x only, similarly S 1 to the power 1, but S 2 to the power 0. So, only S 1, and again here you get 1, okay, and outside also 1 of course. So, this time you get, now take n equal to 2. For n equal to 2, here you have in this summation you have got 3 terms, k equal to 0 first, or maybe you start with k equal to 2, then 1, then 0. If k equal to 2, 2 here and 2 here means actually it will give rise to 1, and x square y to the power 0. So, e x square, similarly S 1 square, but S 2 to the power 0. So, this will give rise to and of course, 1 by factorial 2, that is 1 by 2. So, that will give rise to what? 1 by 2, maybe we can put in a bracket, e of x square, that is m 2 0 S 1 square, then k equal to 1, k equal to 1 means 2 here, 1 here. So, factorial 2 divided by factorial 1 into factorial 1. So, that is give rise to 2. So, we will have a term 2, okay. Then e of x to the power 1, y to the power 1. So, e x y, which is m 1 1, and again S 1 to the power 1, S 2 to the power 1. Then k equal to 0 will give rise to what? 2 0 here will give rise to again 1, factorial 2 divided by factorial 2 into factorial 0, that is 1, and e of y square S 2 to the power 2, right. So, that will give rise to m 0 2 S 2 square plus so on and so forth. So, you see all the moments are present here, right. Okay. Suppose given this moment generating function, we want to find out MKR, that is if k plus r is equal to say some n, then this nth order moment MKR. How do we go about it? So, for that I rewrite that term again, that phi prime S1 S2 Okay. Now, you see one thing, if I differentiate this guy, if k plus r is equal to some n, and if I differentiate these n times, out of which with respect to S1 k times and S2 sorry r times, and then after differentiation put S1 equal to 0, S2 equal to 0. What do you get? Now, let us see how to proceed. First, since k plus r equal to n, consider in this summation n equal to, so if you are confused, if you want rather, if you want I can make it m. So, if it is m, in this case first consider n equal to m, after all n is 0, n is 1, n is 2 dot 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 up to infinity. So, it can be m also. So, take the case n equal to m. So, when n is m from outside, here I have got a binomial series where k starts from 0 goes up to m, total number of terms is m. Here this summation of the two powers, power of x, power of y, that is always equal to m, then m, okay, that is always equal to m, because I am talking from outside, I am taking the particular case where n equal to m. So, n equal to m here, and I have got a binomial series. Okay. So, e of x to the power k, y to the power m minus k. Okay. Now, similarly S1 to the power k, S2 to the power m minus k. Now, suppose I first differentiate it with respect to S2. How many times? R times. R means m minus k times. So, if you differentiate this factor m minus k times, what happens? You do not get any power of S2. Each differentiation leads to reduction of power by 1. First time we differentiate, power becomes m minus k minus 1. Next time m minus k minus 2, so on and so forth. So, if you differentiate it m minus k times, then you finally get S2 to the power 0, that is 1, but a factorial of m minus k comes. So, that will give rise to m minus k factorial. Okay. Everything else remains same in that particular term. Okay. And now, if you differentiate this with respect to S1 k times, again you get S1 to the power 0 in the end, that is 1, but a factorial k comes. All right. There are other terms also in this series. First, you are differentiating them, but remember in this series either you have got this situation where this is k and this is m minus k. If you take some other term, maybe the power here is higher, but power here is less. So, if you differentiate this S2 to the power m minus, suppose you consider for example other term S1 to the power k plus 1, S2 to the power m minus k minus 1. if you consider that term and again differentiate it with respect to S2 m minus k times, obviously you get 0 here, because power is less. Power then because now we have got S1 to the power k plus 1, but S2 to the power m minus k minus 1, whereas you are differentiating it m minus k times. So, obviously this will give rise to 0. So, product will be 0. On the other hand, if you take a term S1 to the power k minus 1 and here S2 to the power m minus k plus 1. So, this power here is higher by 1, for S1 power is less by 1, S1, that is power is k minus 1, and now differentiating with respect to S1 k times, again this factor will become 0, because power is k minus 1, but you are differentiating k times. So, you understand that other terms after differentiation become 0. You even do not have to put S1 equal to 0, S2 equal to 0. Then further I took n equal to m. If it is n equal to m minus 1 or m minus 2 or m minus 3 and likewise, there even it is obvious that powers are less and differentiation will give rise to 0. Okay. I will consider the case where n equal to either m plus 1, m plus 2, m plus 3, that is when n takes higher values. There you will see, there you will get some such terms like this. Maybe consider the case where n equal to m plus 1. So, this becomes m plus 1 minus k, and this is S1 to the power k. So, I agree. I mean, here if you differentiate this product with respect to S1 k times and S2 m minus k times, as here, this product will not become 0. Okay. There will be some term either S1 or S2 or maybe some power of that. Okay. But then we substitute S1 equal to 0, S2 equal to 0, that will take care of that will eliminate them, right. So, you understand that even if I take n equal to m plus 1 or m plus 2 or m plus 3 higher terms and consider the binomial series, do this differentiation. Upon differentiation, if I substitute S1 equal to 0, S2 equal to 0, all terms varies. Only when I am considering this n equal to m and the corresponding binomial series here, and then differentiating every term with respect to S2 odd times and S1 k times, where k plus r equal to m. Okay. So, then that is S2 to the power m minus k, which is r. So, S2 to the power r, S1 to the power k, this is differentiated S2 to the power k differentiated, sorry, S2 to the power r differentiated r times, S1 to the power k differentiated k times. So, both give rise to just 1 and 1 and factorial k, factorial m minus k, but no S1, no S2. So, it does not matter whether put S1 equal to 0 or S2 equal to 0. So, only that term remains. And these two factorials have come up, factorial k, factorial m minus k. Now, consider n k here. After all, what is this? Factorial n, that will be cancelled with factorial n here from outside, and in the denominator you have got factorial k, which will cancel with this factorial k. Another term is factorial n minus k, which will cancel with, well, I am considering n equal to m, that is, let me make the correction. So, it is m k here. Okay. So, factorial m and n equal to m is considered. So, factorial m here. So, factorial m cancels. In the denominator here we have got factorial m minus k and factorial k, they cancel with this factorial k, factorial m minus k. So, what I am left with is basically this term e of x to the power k, y to the power r, where k plus r equal to m. Okay. So, this will give rise to that is m k r, where k plus r equal to some m. This m stands for moment, it is not the m that I was talking of earlier. So, this shows that giving this function phi s1 comma s2, if you are interested in finding out a moment m k r, then you differentiate this with respect to s2 r times and with respect to s1 k times. Then upon differentiation, whatever you get, substitute s1 equal to 0 there and s2 equal to 0 there. Okay. So, we have proved this result. Now, let us see and let us consider an example. Suppose it is given that x and y, they are jointly zero mean. Okay. We have to find out, if the question is show that E x square y square, which is nothing but m to 2, is nothing but E x square E y square plus twice E x y whole square. Okay. Or you can also say equivalently sigma x square, after all mean of x is 0. So, E of x square means E of x minus 0 whole square, that is variance of x, sigma x square, sigma y square here, and obviously this is the covariance C, because what is covariance? Expected value of x minus mu x times y minus mu y, but both the means are 0. So, it turns out to be expected value of just x y, we can call it C. So, this is twice C square. We have to prove this. Now, one thing is this, that since it is m 2 2, what you can do? You can simply apply the previous formula, that is first find out phi prime, the function phi prime as a function of S1 and S2, okay, and then 2 2. So, k equal to 2 or equal to 2. So, k plus r, that is 4, right. So, differentiate that function with respect to S1 2 times, S2 2 times, whatever you get, now put S1 equal to 0 in that expression, S2 equal to 0 in that expression, right. That will give you this, but that will be little cumbersome. So, we follow just little more an approach which is slightly more different, slightly more direct. Okay. Let us see what it is. As you know, we have already seen that phi prime this we have already seen, right, and I am interested in finding out E x square y square. That means, k should be 2, okay, and n minus k should be 2, that is n minus 2 should be 2. So, n should be equal to 4. So, in this summation, from the outer summation I pick up the particular case where n equal to 4, okay, where n equal to 4, and the corresponding term and for n equal to 4 we consider this binomial series. There for one term I get E of x square y square, for what k? K equal to 2. So, first n equal to 4 I fix. So, k equal to 0 to 4, I have got a binomial series of 5 terms. Out of those 5 terms I consider k equal to 2 case. If k equal to 2, then only you have got x square y square, okay, and therefore, we have got it S1 square S2 square, okay. So, you can say remember this S1 square S2 square, this combination, this comes up only in this case where n equal to 4 and then k equal to 2. If n equal to 5, you will not have, if suppose n equal to 5, you got another binomial series from k equal to 5, but there are 6 terms. But in no term you will have a situation like S1 to the power 2, S2 to the power 2, simply because the total, the sum of the two powers must be then equal to what? Since n equal to 5, it should be 5. But when it is S1 square S2 square, then that means total power should be equal to 4, right, n should be equal to 4. So, this combination occurs only, this combination S1 square S2 square, this occurs only when n equal to 4 first, there is 2 plus 2 is 4, and there you take k equal to 2. So, one is 2, other one is 2. Okay. So, I can say that in this infinite series, I have to find out the term, find out the coefficient associated with this term S1 square S2 square. What is the coefficient? The first we have said n should be 4. So, that will be 4 k equal to 2, okay, and from outside 1 by factorial 4 and then E x square y square. Right. So, I erase this. I rewrite it here. So, S1 square S2 square gives rise to this term. Remember, our interest is in this thing, in this expected value, that is E of x square y square. We are interested in this. Okay. On the other hand, so far I have not used the fact that they are 0 mean Gaussian, jointly Gaussian with means 0. Okay. I have only taken the general expression for phi prime S1 S2. Okay, the general expression, whether x y are jointly Gaussian or not, whether they have 0 mean or not. I mean, this is always true that in that moment generating function, that particular term that has S1 square S2 square, okay, that will have this coefficient. So, I have just written down the coefficient. Okay. But now I come to this business that x and y are jointly Gaussian and mean 0. Now, we know, we have already seen earlier that in such case, what is phi S1 S2? Phi prime. In fact, we have found out the characteristic function in such case, okay, and phi prime S1 S2 is quite close to that. J omega 1 and j omega 2 are to be replaced by S1 S2. Okay, that will give rise to this. In fact, you remember, in case you have forgotten, just remember well, I think I have to rewrite it here because that page has gone from here. So, just bear with me, there is some problem here. So, I just have to write down once again S1 square S2 square, that was giving rise to this coefficient. Okay. And now, we are considering this fact that x and y are jointly Gaussian with mean 0. Now, earlier we have seen the characteristic function, joint characteristic function for such random variables. What was that? Phi omega 1 omega 2, we have seen it earlier, that this is equal to e to the power j mu x omega 1 plus mu y omega 2, okay, times again e to the power minus half and no j here, omega 1 square sigma 1 square twice r sigma 1 sigma 2 omega 1 omega 2 plus omega 2 square sigma 2 square. So, you can write down what is phi prime S1 S2. Simply if you remember this moment generating function, the formula for moment generating function is nothing but characteristic function where j omega 1 was to be replaced by s 1, j omega 2 to be s 2. Okay. So, what does it give rise to? This j, and in any case mu x and mu y are given to be 0 here. So, e to the power 0, this term goes, this is 1, and here we get e to the power so j omega 1 is s 1. So, s 1 square is minus omega 1 square. So, minus omega 1 square. Okay. S 1 square is minus omega 1 square. Just a minute. So, I directly write down, in fact, as the book says, this is e to the power minus a, where a is remember twice r sigma 1 sigma 2 is nothing but this r into sigma 1 sigma 2 is nothing but the covariance, because r is correlation coefficient. So, you can say this is covariance C. So, you can say twice C S 1 S 2 plus what? S 2 square, there is sigma 2 square S 2 square. Okay. Now, what we do is very simple. This e to the power minus a, that is an exponential series, right. So, it will be having terms like 1 plus a plus a square by factorial 2 plus a cube by factorial 3 plus dot 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 dot. In this series, I will find out where we get this term like s 1 square s 2 square. Take out the coefficient, equate that with this coefficient, that will give us the result. Okay. So, let me erase this. You see one thing, first term is 1, forget that, because that has nothing to do with s 1 square s 2 square. Second term is a means this term, but it has either s 1 square or s 2 square, but s 1 s 2, no s 1 square s 2 square together. So, forget that term too. Then s square by 2. Now, in s square by 2, we have the square of this. In the square of this term comes. So, there is one case where you have got s 1 square s 2 square and a product of these two, that also has s 1 square s 2 square. So, in s square by 2, I get this s 1 square s 2 square term. Okay. How about a to the power 3? Okay. In a to the power 3, of course, you will not get it, because obviously you see either this is raised to the power 3, each is raised to the power 3, okay, or square of this times this, or square of this times this. So, you will not get, you can easily see you will not get s 1 square s 2 square. Okay. So, only a square by 2 is where you get this term s 1 square s 2 square. What is a square by 2? Remember how I am getting a square by 2, that is I expanded e to the power minus a, okay, into its power series. In fact, it should be to the power plus a, you remember, because in the characteristic function we had terms like minus omega 1 square, minus omega 2 square, and if s is j omega 1, then s square is minus omega 1 square, s 2 is minus j omega minus omega 2 square, and s 1 s 2 is minus omega 1 omega 2, right. So, it should be actually plus. Okay. Now, s square by 2 comes as the third term of the exponential series. First is 1, forget it, it has no such term s1 square s2 square. Second is a, again that has got no term like s1 square s2 square, forget it. Only the second term, so third term, which is a square by 2, that will have expressions like s1 square s2 square. Okay. I mean, a square by 2 means 1 by 8, 1 by 2 and whole square of this 1 by 4, 1 by 4, 1 by 2, 1 by 8 times this whole square, right. In this expression now, just find out when, on what occasions you get s1 square s2 square. First whole square of this, that will give rise to s1 to the power 4, forget it. Whole square of this, that will give rise to s2 to the power 4, forget it. But whole square of this, that will give rise to 4 c square s1 square s2 square. So, I take it. Okay. 4 c square s1 square s2 square. So, this time I am getting 4 c square by 8, 1 by 8 is common. So, one term is 4 c square, and there will be a term like twice this and this, that will give rise to s1 square s2 square, but twice sigma 1 square sigma 2 square. Okay. So, twice sigma 1 square sigma 2 square. So, this is what I will have with s1 square s2 square in this term a square by 2. In a square by 2 there will be several terms, but s1 square s2 square will have this coefficient. So, these two are to be equated. These two are to be equated, okay. This one and this one. If you equate this, you directly get the result. After all, you get factorial 4 here, that cancels with factorial 4. In the denominator, you have got factorial 2, which is basically 4. So, 1 by 4 and here 1 by 8. So, that cancels, you get only 1 by 2, which means e x square y square is 1 by 2, 4 c square plus twice sigma 1 square, sigma 1 or rather sigma x, sigma y, sigma x square, sigma y square. You can write sigma x square, sigma y square plus twice c square. This is what we wanted to prove, right. So, we have proved it. So, that is all about this moment generating function. Another thing we want to do, that is joint okay. That is either z is a function of x y, that is a function of single function of 2 random variables, or you have got maybe 2 functions z and w, 2 defined functions of 2 random variables. In both case, you can say that if z, some capital Z subject to the event m is same as probability of z taking value capital Z less than equal to capital Z along with m. So, this joint event, both m taking place and this event taking place, that is Z taking value less than equal to capital Z divided by probability of the event m. So, this is the case for a single function of 2 random variables, and you have got, when you have got 2 such functions Z and w, capital Z capital W by m by the same token will be this joint density. Okay. Okay. Let us take some example. Suppose z is y, z is a function of x and y, but z is suppose y, and that event m is nothing but x taking values less than equal to some capital X. That means we have to find out P y sorry here I mean we will find out this conditional thing. Okay. This is nothing but probability of this joint probability is y taking values less than equal to capital Y, x taking values less than equal to capital X divided by the probability of x. The probability this is the joint density we know, this is joint distribution f x y, you can say x y, and this is f x x. So, how about the density? That is more important. Density is not simply derivative of this with respect to y. Okay. So, that means subject to this is nothing but okay. We modify this example, make it slightly more general now. Now, two functions z is y, w is x, and m is this thing x less than equal to some x 2, x 1. Okay. So, here what is subject to this m? This is nothing but probability, this joint probability of x sorry okay. Now, you see one thing, suppose you choose x, we have got two limits, we have got two limits, one is x 2, another is x 1. Now, if this capital X is such that it is less than x 1, this x 1 limit. So, the two things are jointly occurring, x has to be less than equal to some given capital X, at the same time x should be greater than x 1 less than equal to some x 2. Now, if this capital X is less than or equal to x 1, then two things cannot be together, cannot take place together, right, that x is simultaneously above capital X 1 and less than equal to x 1, that is not possible. So, if x is less than equal to x 1, this is 0. Similarly, if x is greater than x 2, then what happens? If x is greater than x 2, then x is less than equal to x 2, I mean x is less than equal to capital X and x is less than equal to capital X 2. Out of these two, I will consider this condition, because capital X 2 is less than x. So, in that case, it is simply because joint probability of y falling less than equal to capital Y and x lying within this range. That will be nothing but what? The distribution x 2 y and divided by, this is of course f x x 2 minus f x x 1. Okay. I am nearly through, just one more expression and that will be over for today. And the other case, is if x is lying within this range, if x is then obviously I will take small x to be greater than x 1, but less than equal to capital X. Okay. On the lower side limit is x 1, but the upper side it will go up to capital X as coming from here. In that case, it will be similar to the previous one. Now, to find out density, you will see one thing, that in one case we have got 0. So, density will be 0 because derivative after all. In the other case also, if you find out that this is a constant thing. Okay. After all, joint density means what? I mean, you have to take partial derivative del square f del x del y. There is no x here, this constant. So, derivative will be 0. Only here there is x. Okay, only here there is x. So, only here you will get this density. Okay, and what will the density be? This is independent of x, and here del square f del x del y will give rise to p of x y. So, here p of x y divided by whatever we have here, this constant. In the other two cases it will be 0. Okay. So, I stop here today, that is all for today, and in the next class we start from here. Thank you very much. Okay. So, today we discuss an important topic, that is, in fact we start this topic, sequences of random variables. You see, we started with first a single random variable, right, and we considered a function of a single random variable. Then we generalize it to, I mean, two random variables. Okay. So, you can even say that it is a sequence just of two elements, two random variables, two element sequence, and we consider a function of two random variables, then two functions of two random variables and all that, right. That whole treatment will now be generalized, where we will be considering a vector, say x as x1 dot 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 xn. This x will be called a random vector if each element x1 to xn is a random variable. That is, x will be called a random vector or say sequence if each xi is a random variable. Okay. So, you see earlier we considered two random variables. So, we had a vector of two elements x1 and x2, we call it xy, this is defined notation, but now it is more general n such random variables, right. So, from a hindsight you can see that if you talk of the joint density or joint probability distribution of x, it will be basically a function of n variables, right, x1 to xn. Okay. So, we can define joint probability distribution actually I should write like f x where x say takes values x1 to specific values x2 dot 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 xn. Okay. And this capital X actually is a vector consisting of the variables small x1 dot 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 small xn. Here capital X1 is a particular value for small x1, x1 is the variable, capital X2 is a particular value for the variable small x2 and likewise. What does this mean? It means the probability of this event, that x1 is less than equal to capital X1, x2 less than equal to capital X2 dot 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 xn less than equal to capital Xn. This should occur jointly. There are n joint events. There is one is small x1 less than equal to capital X1 and there is small x2 less than equal to capital X2, so on and so forth. Okay. This should occur jointly, simultaneously. That is why it is called joint distribution, right. Okay. This is denoted by fx x1 up to xn. Sometimes when I do not need, I may skip this subscript x and directly put x1 to xn. I think you can easily understand, okay, sometimes. But when there is confusion, when suppose I am dealing with two or more than two such distribution functions, then to differentiate between the functions I may put the subscript. Okay. Now, this is for the joint probability distribution. By the same token, you can then define and you can easily see that this is now a function of n variables, okay, x1 to xn. By the same way, I can next define the joint probability density function. Joint probability density. This simply you know that we have to differentiate the joint probability distribution function. So, we define like this Px x1 up to xn is nothing but del n times, okay. I am skipping the subscript here, x1 dot 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 xn with respect to del x1 del x2 dot 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 del xn. This is the joint probability density. What does it mean actually? It means that if you now consider an n dimensional space whose x's are x1, x2 up to xn, and there if you take an infinitesimally volume, I mean mass, okay, infinitesimal zone, region, okay, whose volume is say dx1, dx2 up to dxn, that is along x1 axis, that is suppose in an n dimensional space you are located at a point up to x n, at this point you are considering an infinitely small or infinite small region or cell, okay, whose sides are, we call it actually hypercube. Actually in real life cube means it has got only 3 sides, okay, but in an n dimensional space I will call it n dimensional hypercube, whose sides are dx1, dx2 up to dxn. So volume is this. So basically it defines an area where x goes the variable x1 goes from capital X1 to capital X1 plus dx1, okay. Capital X2 goes for, that is this zone, this for variable x1, then for variable x2 again this is the range, dot dot dot, okay. You can easily see will be nothing but Px at this choice x1 up to x n divided by the determinant, that is 1, and we are given the fact that the random variables x1 up to x n, they are independent, okay. So this joint density is nothing but the product of the individual densities. So p x1, okay, and capital X1 is y1, p x2 which is y2 minus y1 dot 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 p x n y n minus y n minus 1, okay. So you can easily see that the concepts involved here, they are nothing new. They are simple generalizations of the concepts that were valid or that were introduced rather in the case of 2 random variables, okay. That is why I am not giving any proof and all that, you can argue about this on your own. So I stop here today. In the next class I consider this issue further and go into things like mean, covariance, correlation. In fact, we will have a correlation matrix now, covariance matrix and things, okay. Again the characteristic function issue as relevant here, and that takes us to a very important theorem called central limit theorem, okay. So that is all for today. Thank you very much.